Okay, so today we're going to work on counting and probability. And so we'll start just kind of reviewing a couple things that you did for the homework today. Like, do you remember the 2 dice, when we tossed 2 dice? Do you remember how many were in that sample space? We listed them all. 36, yeah. Okay, so what we did there was we said on the first toss, there are 6 outcomes. And then on the second toss, there are also 6 outcomes. And so what we did was multiply that together. And that's the first thing in this section is the multiplication rule. It just says you multiply the number of outcomes for each time that you do something in your experiment. Okay, so we got 36 there. So if you flip a coin 3 times, how many outcomes should there be? There's your 3 flips. How many options are there each time?
2.
So 2, 2, 2, but what do? Multiply, which would be what? 8.
Wait, 8?
Yeah. Right, 2 cubed, yep. So 8 outcomes, right? Think about what those looked like. There was 3 heads. You could do heads with 2 tails, but that could happen one of 3 ways, right? The heads could be first, middle, or last, right? That's 4 of them, and then it could be 3 tails, 2 heads and a tail. So you could, write it out if you had to. But this counting method just makes it easier when you need to do a probability and you just need to know how many are in there, right? Because when we do the probability of an event, the denominator is always how many are in the sample space, right? So back here, the 2 dice, do you remember the probability sum of 4? How many ways could the 2 dice add up to 4? 1, 3, 3, 1. What else? 2, 2. And you only counted that once, right? Yep, so 3 out of, 36. Yeah, that's why we need the 36. And then with the coin flip, we said, what's the probability of getting all heads? Yeah, if you know how many are in that sample space, then you can just count up how many are like that. Okay, so let's say you're taking a true-false quiz, 5 questions. 5 questions, true-false. How many ways could you answer that? So you guess at each one. Guess at the first one, how many choices?
2.
2. Second question, third question, fourth, fifth. So how many ways could you answer that? 32. All right. What's the probability you get them all right? So how many answer keys are there? 1. Yeah. So probability if you're guessing, you get them all right, 1 out of 32. Okay, so the other one that works like this, so there's the coin flip that has 2. There's true-false question. There's also the birth order in a family. So if I said how many 5-child families are possible? And what I'm talking about there is like, are they all boys? So that would be one of them. It could be 1 boy with 4 girls, but we care the birth order. So that boy could have been first or second, right, with a bunch of girls, or third or fourth. So you're counting all of those, right? And then you do 2 boys, 3 girls, and so how many would there be altogether? Each birth,
32.
Yeah, same thing, right? Each birth, 32. Okay. So I come from a family of all girls, and there's 5 of us. Yeah. So what's the probability of an all-girl, 5-child family? How many out of 32?
1 out of 32.
1, yeah, 1 out of 32. Okay. My mom came from a family of 6 girls, no boys. So she's one of 6. She's got 5 sisters. So how many 6-child families are there? Tack on another 2, right? For the 6th birth, what would that be, 64? 64 of them. So what's the probability of all girls there? 1 over 64. Okay. So she started this, right, with the 6 girls. And then she has 5 girls. And then we have kids. So I'm kind of like taking a little leap here. But let's say all of the grandkids are a family. There's 8 of them. Okay. So let's call it just an 8-child family for the grandkids. First of all, how many of those would there be? So we had 6. We need times 2 times 2. What's that get you to? 256. Okay. Guess what? No, they're not all girls. There's 1 boy. There's 1 boy and 7 girls. How many 8-child families would have 1 boy?
1 out of 256.
More than that, because the boy could be first, right? With a bunch of girls. Or he could be second, or third, or fourth, or fifth, or sixth, or seventh. So there's 8 of them. Yep. So there's 8 ways that could happen. 8 families that would have 1 boy and 7 girls, right? Because he could be born first, second, third, fourth, all the way up to 8th. Okay, so there's 8 of those. So what's the probability of that situation? Probability of 1 boy and 7 girls. 8 out of 256. Okay, now, these different events are supposed to be independent, right? Just because my mom had only sisters doesn't mean she should have expected to have only daughters, right? And so if you count these 3 as independent events, then what's the final probability of her having 6 girls in her family, and then giving birth to 5 girls, and then having 8 grandkids with only 1 boy? What's the probability of all of those? How should I figure that out? I got these. This is the first one. This is the second one, and there's the third one. Pick one. Do you want to add them or multiply them? Multiply, yeah. Because you want this and that, and then that, right? So let's do that on the calculator. So you can take, what, 1 out of 32, and we'll multiply that by 1 out of 256, and then multiply that by the 8. Wait, did I do that right? It was 8 over 256. What's in the middle here? 64, thanks. 64. So I'll get rid of that. All right, and then the 8 divided by 256, right? Okay. What is that number? Can I have a probability 1.5? Can't be over 1, right? So what kind of notation is that? Scientific, yeah. So just be careful on these if you haven't done scientific notation in a while, right? With these really small probabilities, that's going to pop up. And so always look to the end, right? This one, 1.5, and then the calculator says E negative 5, but that means times 10 to the minus 5, right? So if I want to convert that back to standard, do you remember what to do there? Move the decimal which way? Left. Yeah, left 5 places. So 1, 2, 3, 4, 5, and then fill in with zeros. So the likelihood of that scenario over there is 0.000015. Yes, I figured that out at Thanksgiving one year. No one else cared, but.
Must be a boring thing or something.
Well, yeah, my sisters weren't excited. Okay, so that kind of gets you, the connection, I guess, between counting and then being able to do probability. All right, well, there's 2 other kinds of counting techniques. Let's start, though, with figure out an ATM code. How many ATM codes you could have? We need 4 numbers, right? How many choices for each one? 10. Because each number could be 0, 1, 2, all the way up to 9. Yep, so 10 choices there. Is it okay to have 2 of the same number? Yeah. So 10 there, 10 there. Okay, so 10,000. Yep. What if I tell you you can't repeat a number for some reason? You have to have 4 distinct numbers, so no repeats. Now how many are there? I'd start with all 10 options, right? But then let's say I use a 2. I can't use it now. So it'd go to 9, yep, 8, 7. So I'd multiply that together. Yep. I think that's 50, somebody do that, 40, 50, 40? Okay. So let me ask you this too. Does order matter? So like if I pick the ATM code 5231, but I punch in 5213, is that gonna work? No, okay, so order is counted. Order is important, right? So these things do count the order. It counts, when it's coming up with 5040, it's counting this one as different than this one. So not only does it pick the 4 numbers, but it rearranges them. It permutes them. And that's the other kind of counting rule that we have, is a permutation. So if you have unique numbers, right? If you can't use your objects more than once, and if order is important, then you have another option from the multiplication rule. You can use a permutation. Okay, so I'm going to show you the formula for it if you're interested, just so you know what your calculator's doing, but you'll be able to use your calculator on this. And this is what it'll look like. There's a capital P, and then to the left subscript, you say how many choices you had. So when I was picking that ATM code with no repeats, I had 10 choices, right? And I needed 4 numbers. So this is read permutation 10, choose 4, okay? And here's what the formula looks like, in case you're interested. Do you know what that means? Have you seen that math symbol before? Not just that I'm really excited about 10, but. Yeah, it's factorial. Have you heard of that? Yeah, 10 factorial over 10 minus 4 factorial. So the formula, just in general, is permutation n choose r, n factorial over n minus r factorial, yeah. So factorial means 10 times 9 times 8. So if I were to write this all out, and you just keep going until you get all the way down to 1, okay? What's 10 minus 4? That'd be what, 6 factorial? 6 times 5 times 4 times 3 times 2 times 1. See what cancels? And so now it looks just like what we did over there. So there's going to be a big overlap between the multiplication rule and permutations. They both count the order. Yep. So you end up with those 4, which is what we had over there. So you can pick either one in those instances. But let me show you on the calculator how to do that. So let's see, you're going to be in the math menu, and then look for the probability. Or yours might just say PRB. So the math menu, and then get in the probability submenu. And you got a couple choices there. Yeah, there's just a regular factorial if you wanted to figure out that 10 factorial. Yeah, and the C we're going to do in a minute. That's a combination. And then the one we're doing now is a permutation. So what you have to do, though, is you have to key in the first number before you get into this menu. So it wants the 10 first, and then we'll come back here and pick that, and then we'll do the 4. Okay, so I'm going to get out of here. Just quit out of there, do the 10, and then go to math, probability. Pick number 2. Now, if you have a newer calculator, it's going to do this. But the older one, it'll just say 10, and then what's it say, NPR? Yep. So some of them have the ability to make it subscript, and some don't. But either way, you just type in the second number, and then hit enter. Any calculator problems there? Okay, so let's stick with permutations for just a little bit. I'm kind of rearranging my office after 25 years, getting rid of a bunch of books, and so I'm making an arrangement. This is a true story. I'm arranging books on my shelf, okay? And I have 5 books to choose from. Okay, maybe I'm fabricating it just a little bit, but so I've got a calculus, a pre-calc, a statistics, let's say an algebra, and a trig. Those are my 5 books, right? 5 distinct books. And I want to arrange all 5 of them on a shelf. Okay. So 5 distinct objects. I'm telling you order is important by saying that I want to arrange them. So you have to look for those words that kind of say to you that order is important. Otherwise, I could just throw them up there. There's one way to do it. Right, so arrange all 5 on a shelf. How many ways can that be done? So how many arrangements are there? What do you think? If I told you, since arrangements, since order is important, I want to do it with a permutation, then how many do I have to choose from? 5 books. How many do I want to arrange? All 5, yeah. So that's how it would look with permutation. Although you would have that other option, right? Multiplication rule, you're just looking at the first spot on your shelf and you have 5 books to choose from. Well, once you put one there, you can't use it again, so now you only have, right, 4, 3, 2. By the time you get to the end, there's only 1 book left. So that would be fine. You could do it that way. If you notice on the permutation formula, this would be 5 factorial over 5 minus 5. So 5 factorial, which looks like something you shouldn't be able to do in math, but we define 0 factorial to be 1 so that we can do stuff like this. Yeah, so 5 factorial and that, they're the same thing. Yep. Is that the What do you get for that? 120, okay. So if you want to arrange all of something, then you could just take 5 factorial too. That would even be a shorter way to do it. If I said there's 7 kids and they're lining up for the bus, right? How many ways can they do that? And they care about order, right? It matters who's first and who's second. And then you would just say, oh, well, that's permutation, 7, choose 7. Yep, just 7 factorial. Okay, so let's stick back with the books here for a minute. Let's say I only have room for 3 on this shelf. So I have 5 books, and I want to arrange 3 of them. So it would look a little bit different if I was doing a permutation, right? 5, choose 3. Or 5 times 4 times 3, right? Stop. Either one should work. So practice, on your calculator, 5, choose 3, and make sure you're getting the same thing. What would that be? 60? Okay. So what if I don't care about the order? So, because this, what this did is, let's say it picked calculus, statistics, and trig, right? It picked those 3, and then it said, well, wait a minute, that's a different arrangement than statistics, calculus, trig, right? Which is different from, I don't know, if the stats was first and then trig and calculus, right? How many arrangements of those 3 are there? Calc, trig, statistics. What did I miss? Trig first? Calc, statistics, trig. There's 6 of them. So in those 60, not only is it picking out the 3, but it's permuting them. So what if I don't care about that? I just want to take 3 of them on a trip, because I have to bring my math books on a trip, right? So I have 5 books, and I need to choose 3 to pack in a suitcase. Okay, so now if I pick this group of 3, do I really need to count it again? 5 more times? It's doing the same thing, right? I'm just throwing those 3 in a suitcase. I don't care about the order. So when order is not important, you don't want it to keep counting. Not important. Important. There we go. You don't want it to count it once it gets its groups. That's a combination. So you would pick combination 5, choose 3. Right, so when order's not important, but you still have distinct objects like that, that's when you're going to pick combination. Okay, let's see if I can fit the formula up here. So combination n, choose r, starts out like a permutation, n factorial over n minus r factorial. But it divides by those permutations. So it takes out that extra part. So r factorial. So see what it would look like for the 5, choose 3. 5 factorial over 5 minus 3, 2 factorial, times 3 factorial. So 5, 4, 3, 2, 1, 2, 1. 3, 2, 1. All right, it takes out those extra 6. See, it's dividing that out of there. So just 20 over 2, now there's only 10. So there's 10 groups of 3 books that I could pick. Right, so your number of combinations is always going to be smaller than the number of permutations. Okay, let's just double check that on the calculator. Make sure you're working that through. So let's see, combination 5. So you do the 5 first. 5, and then math, and then probability, number 3, and then we need 3. Yeah, so bigger number is always going to be first, and then enter. Okay, questions so far? Okay, let's say you have a committee and there's 8 people on it. Okay, so I have 8 people in a group. 2 of them are no, let's go 3 and 5, yeah. So we'll go 3 are administrators and 5 of them are faculty. Okay. From those 8 people, I need 4 people to go to a conference. So how many groups of 4 can be chosen to go to a conference? So you'll get a question like this. You have to decide for yourself, is order important? Right, so you don't want to just start saying, oh, well, I'll pick the first person to go. How many people are there altogether? 8. You wouldn't want to do the 8 times 7 times 6, because that's going to count the order. That's what you have to remember, is that multiplication rule counts the order. So you really only have one choice on this one. Has to be combination, just because it's a group and you don't care about the order. Okay, so lump everybody together, 8 people, and pick 4 I wanted, right? Okay, so let me do that on the calculator. 8, math, probability, combination, 4. 70 different groups of 4. So that's counting, like, I guess it could end up that they're all faculty, right? There's enough faculty that maybe all 5 or all 4 of them end up faculty. So now I'm going to be more specific. How many groups could you get to go to this conference? So how many groups of 4 consist of 2 administrators and 2 faculty? So I'm being a little more specific, right? I want to see how many would have that makeup when it's all done. So what you're going to do there is just kind of break it up. Break it up into 2 stages. Let's choose the administrators. And then we'll choose the faculty. Choose. Okay, so you've got your 3 administrators, right? And you need 2 of them. Do you care about the order? No, they're doing the same. They're just going to the conference. So combination, what do you think? How many administrators? 3. And we need 2. Yep. So you're going to deal with that first. Then choose the faculty. So go in and just look at the faculty. There's 5 of them. Choose 2 more. Okay. Let's go ahead and figure those out. What'd you get for combination 3, choose 2? 3, yeah. Because each time you leave 1 person out, right? So 3 there. How many here? 10. Okay, now you have to ask yourself, when you're all done with this, do you want to have 2 administrators or 2 faculty? Or do you want 2 administrators and 2 faculty? Or and? And. So what do you think you do here? Multiply. Yep, it's a 2-stage event. If you think about your multiplication rule, right? You're doing this first and then this. Yep, so you're going to multiply them together. Okay, so there's 30 of those groups of 4 that could look specifically like this. So the probability part of it would be, what's the probability that I end up picking 2 administrators and 2 faculty? You see why first you had to count up how many just non-distinct groups of 4 there were. There's 70 altogether, and that has to be your denominator, because that's what you have to choose from. And then what goes in the numerator? Yeah, the 30 that you figured out. Yeah, 30 would look like that out of the 70. Yep. Guess I could reduce that 3/7. Okay, questions so far? All right, let's just, now that you've got those 3 methods, right? Multiplication rule, permutations, combinations, let's just work through a couple. I've got these posted in Blackboard too. Let's start with that first one. Zip code has 5 digits. How many zip codes if each digit can be 0 through 9? Kind of like our ATM code, right? So how many choices for each digit in part A? Yeah, if you allow repeats, then you'd have all 10 digits. Yep. So 10. And zip codes, you do care about the order, so that's good that we're doing that. Okay, so 100,000 of those. Now, let's say the first digit has to be a 4. Okay, so here's my first spot, and it must be, I'm not putting how many choices there are this time, I'm just saying that's my only choice. So if I was looking at how many choices I had there, it's 1. Yeah, so that's a 1. But the other 4, it didn't say anything about, right? So those could still be any of the 10 digits. So now how many are there? Yeah, 10,000. Yeah, so if they ever kind of restrict one of them and say it's got to be this, then that just kind of takes that one out of it. Yep. All right, let's do 2. Although we kind of did one like this. You forgot to study. And you're going to take this true-false quiz, 10 questions. How many sets of guesses are there? Is it 20? How many times do you have to make a decision? So you're staring at this quiz. 10 questions. Right. How many choices each time? Do you multiply or add? Multiply. Yeah, there's way more than 20. I mean, think about it. Even if you just put 1 false in there and the rest are true, that false could go first, second, third, fourth, right? And then you'd look at all the ways that you could have 2 false in there. Yeah, there's, is it 1,000? 24, thanks. Yeah. Okay, so 1,024 ways you could answer that. What's the probability you get them all correct? Yeah, 1 out of that. Figure that out in a decimal. It's pretty small. Okay, number 3. So for winter semester, you have to choose a math class, an English class, and a science class. There's 4 math, 7 English, and 4 science, and they all, fit perfectly into your schedule, let's say. How many different schedules can you create? So how many times do you have to make a decision on this one? Choose, what did I put first? Math. Choose math, choose English, choose science. 3 times I have to make a decision. How many choices for math? 4. What was here? 7 and 4. And then what do I do? Multiply, yeah. So that's just straight multiply rule. Yeah. You'll see a lot of times the problems like that will be Like you're gonna order a breakfast and there's 4 different eggs you could pick and 7 different kinds of potatoes or something. That's a lot, but, and then 4 different kinds of toast. How many meals can you make? You just multiply them together. Yeah. What do you get for that? 112? Okay. Okay, let's do a few more. So notice multiplication rule is sometimes the only option you have. If you've got something used more than once, you know, if there are repeats, like I could have several of those trues, that's the only way to go up. Permutation won't work over there. So permutations and combinations, you can't use the same thing twice. Yeah, so there are times when you really don't have any other option. All right, let's look at number 4. So you're going to pick a president, vice president, and treasurer from a group of 11 people. How many ways can I do that if you can't make the same person be like president and vice president? So I can't repeat, right? I can't use all 11 each time. Once I pick somebody as president, let's say, president, vice president, treasurer. Is that what I had there? Yeah. So there's my 3 times I have to make a decision. So what would go in the first spot? 11, 10, and 9. Yep. What is that, 990? Right, so that is counting the order. Like if I pick Amy and Bob and then Carl. That means that order, I'm saying Amy is the president, Bob is the vice president, and Carl is the treasurer. So I still want to count the other orders of that group of 3 people, right? Like if Bob got picked first, now he's president, and then Amy, and then Carl. So if I had to pick one between combination and permutation, which one would it be? Permutation. So the other thing you could do there is say, I've got 11 people, and I need to pick 3. Yeah, so you could do it either way. Yep. So practice that on your calculator, too. You should get the 990. Okay, so what's different about number 5? I still have 11 people. I want to pick 3. Is it a permutation? Why? Yeah, order doesn't matter. So if that group that you're picking is all doing the same thing, don't count the order. Yeah. So it just says a group of 3 students are going to be on a committee. Right? It didn't designate one of them's going to take notes and the other one's going to be in charge of snacks. And, you know, it didn't designate a specific duty for each one. Yeah. So 5 would be combination. 11 choose 3. So there should be quite a few less, all right, because you're not permuting them once you get them. Did anybody get that? 165, thanks. Okay, so far? Okay, well, then you see some repeat of some things that we've done. How many 5-child families? So we said, but we'll just run through them real quick. So for number 6, we had 32. How many consist of all girls or all boys? So the number of all girl or all boy. So think about what those 32 looked like. How many of them look like this? 2, yeah. And the or, you can just add. Yep, there's 2 of them. Okay, So what's the probability a 5-child family has either all girls or all boys? All boys. 2 out of 32. Yep. Yep. So that would work like that. I counted them up. That also would have worked if I had just done, I mean, these are mutually exclusive events, right? So the probability of all girl, so I'll say 5 girl or 5 boy, since they're mutually exclusive, should just be the probability of 5 girls plus the probability of 5 boys. Yep, so I could have done 1 out of 32 plus 1 out of 32. Yeah, so that's the same thing, right? 2 out of 32. What's different about 9? Yeah, it's and instead of or. So if you have a 5-child family, can all of them be girls and all of them be boys at the same time? So what's the answer? 0, yep. Yep, they don't intersect. Those are mutually exclusive like we were talking about. So yeah, that would have to be 0. All right, let's just do a couple more, probably. Oh, I forgot about trees. Yeah, we got to do that. All right, how many ways can 3 children be chosen from a group of 24 to clean erasers? So you have to decide from the wording whether order is important or not. What do you think? It's not, yeah. It's just 24, and you're going to pick, how many did I say there? 3? Yeah, so I would do 24, math, probability, pick combination, and then 3. Yeah. So I'm not going to ask you for that formula on a test or anything. You can just use your calculator. So 20, 24, bunch of them. How many ways can 5 magazines be chosen from a group of 8 just to take on a trip? Combination, permutation. Combination, yep. 8, choose 5. Yeah, you'll know if you happen to mix those up, your calculator will give you an error. So it knows that you need the bigger number first. Yep, so 8, math, combination, how many? 5? It's 56. 56 different ways that you could do that. Okay, how about 12? How do you know that order is important?
It's literally like about the order of the 2.
Yeah, yeah. They're lined up. Yeah. Oh, Joan, my mother would, yeah. Okay, so if it's whichever ones need the sun coming from that direction at this time of day, that one's got to go there. And then that one, and then that, right? You don't put the cherry tomatoes there, they're gonna climb too hot, you know. So if it says lined up, that means order is important, yep. And I wanna arrange all 5 of them, right? I've got 5 spots for them. So what should I do there? Permutation, 5, choose 5. You want all of them lined up. And remember the quick way to do that? It was just 5 factorial. Yep. What is that, 120? Yeah. Okay, so 13, I want to put 5 varieties in there, but I've got 8 that I have to choose from. So what's that one going to be? 8, choose 5. Still care about the order, yeah. Yep. So 8, math, probability, permutation. Choose 5. 6720. Yep. Okay, kind of got the idea then with the permutations combinations? Okay, last thing in this section, they do talk about probability trees. It's just a way of keeping track of that multiplication rule. So like in 14, it says you toss a fair coin and then you roll a die. How many outcomes do you think there would be? So think of it as a two-stage event, right? Die, wait, which one's first? Coin. Do the coin and then the die. How many outcomes on the coin? 2. Die? Okay. So 12 ways to do that. Yeah. Now, show that with a tree. So a probability tree just says, you're going to start at the beginning of your experiment with a dot, and you flip the coin, right? So you give 2 branches, 1, 2. And you label it with what they are, heads, tails. If it's a probability tree, it's also got to have a probability on the branch. So each one of those, it's a fair coin, would be half, half. So that represents the first part. And then the second stage, you just add that on. So from here, I would be doing 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Label them. And then probability, what's the probability of each? 1/6. Yeah, I'll just, since they're all the same, I'll just do that. 1/6, like that, okay? Then at the bottom, you put in what are the final outcomes. So if I follow this path, heads followed by 1, then my outcome, heads 1. Or I could get heads 2, right? And then tails 1, tails 2. So these are all the final outcomes, right, just listed. There are 12, like we said there should be. And what's the probability of each one? 1/12. They're equally likely. Yep. What's the other way you could have gotten that? I mean, I know there's 12 of them, so they're equally likely. Each one has a probability 1/12. But what if I went back here and said, okay, the probability of heads followed by a 1, a half, and then a 1/6. Multiply. Yep. Because I want this to happen and this to happen. Yep. So that's the other way you can get your final probabilities. Yep. Is just multiply the probabilities on the branches. So that's what we're going to do when the events are not equally likely. So, last example. We're going to look at, let's do marbles. So let's say I have 10 marbles in a bag. Let's go, 3 of them are red. 2 are yellow, and 5 of them are green. I'm going to pick one. So choose a marble and keep it. And then I'm going to choose a second marble. So that's my experiment. And I want you to show that experiment with a tree. So we're going to make it into a probability tree, right? Whenever you do one of those, you need to include the probabilities on the branches. Also, include the final sample space, right? Include the final outcomes with their probabilities. So there's quite a bit to it, other than just drawing the branches. Okay, but I only care about color. They're all the same except for color. So I don't care which red I get, it's just that it's red. So when I start this tree, should I do 10 different branches or 3? Probably be more clear if I said, note the color. right? That makes it clear that all I care about is color. And how many colors are there? Yeah, just 3. Okay, so we'll start out our tree with 1, 2, 3 branches. I could get red or yellow or green. All right, so what are the probabilities there? What's the probability I get red? 3 out of 10. Yellow? 2 out of 10. And green? 5 out of 10. Notice I'm not reducing anything. I really suggest you don't reduce it. It's good to see how many there are, and then in the next stage, remember, you keep the marble. So it's good to watch those denominators go down. Could you pull that shut? Thanks. Okay, so second stage, I could have gotten a red on the first, right? Could I still get a red the second time around? Yeah, because there's still 3 of them. So I could also get a red here, and then a yellow, and then a green. Okay, but you have to remember I kept that marble. There aren't 10 in there anymore. There's only 9. So each denominator here should be 9. And I know that I got a red on the first. That's why I'm over here, right? So if I got a red on the first, how many red are left? 2. What about the yellow and green? Yeah, they're all still there, right? The 2 yellows are still there, and the 5 green. Okay, what does that add up to? Nine out of 9. Yeah, that's a kind of a way to check it, that you did it right. Right, that's all possible outcomes at that point. So make sure that adds up to 1. You know, up here, make sure those add up to 1. Just kind of check it as you go. Okay, let's finish it. So the yellow one, we could have gotten yellow, and then we'd still have 3 options: red, yellow, green. So put those on there. And then their probabilities. Everything on this level is going to have 9 as a denominator. Okay, if I'm in this middle part, how many reds are there still? 3, right? I didn't get that. So I've got all 3 red. It's the yellow that I got, so there's only 1. Yeah. And then the greens are still there. And notice that adds up to 9 over 9. Okay, last one. You could have gotten green followed by red, yellow, green. Red, yellow, green. All 9s. It's the green one that would change this time, because if I'm over here, that means I got a green on the first. So those 5 aren't still there. There's only 4. Okay, but all the reds are there, and the 2 yellows are there. And again, those add up to 9 over 9. All right, we're almost there. Here's the last part. Include the final outcomes. So what I want is a list of the final, when you're all done with this experiment, what are the possible outcomes? I could have gotten red, red, or a red, yellow, or a red, green, right? So just following these paths. In the middle, I could have gotten a yellow followed by a red, 2 yellows, yellow, green. And then down this path, I could have gotten green, red, green, yellow, or a green, green. So that's my sample space. And then the last thing is, what are the probabilities of each one of those happening? So what do you do with the probabilities on the branches? Multiply. So you want this to happen and this to happen. So I need to do the 3/10 times 2/9. 6 over 90. And again, I strongly suggest you don't reduce it. You'll see why when I ask the next questions. Yep. So that one's 6 over 90. Basically, you're just multiplying straight across, right? So the next one would be 6 out of 90. Yep. 3/10 times 2/10. Next one, 3/10 times 5, or that was 9ths, right? 3/10 times 5/9. 15. And you can see why I'm not reducing. I want to make sure when I'm all done that I get 90 out of 90. All right. Okay, what's next? Yellow, red. 2, 3, 6. Should be the same as getting red, yellow. Yep. Just the other order. How about yellow, yellow? That only happens, what, 2 out of 90? And then yellow, green, 10 over 90. Okay, finish it up here. So green followed by red, multiply 5/10 times 3/9. 15 over 90. It's in the middle, 10. And finally, green, green. Yeah, that should have the highest probability. Okay, so 20, 30, 45, 55, 70, 82, 84, 90. Yeah, just double check that they all add up. So that's a probability tree. Then I'm going to ask you things like this. So now that you've got all that done, let's say you're all done with this experiment. What's the probability that you get 0 red marbles? No reds. So that can happen how? Yellow, yellow, because all these have reds, right? Yellow, green, green, yellow, green, green. Can happen one of 4 ways. Either I've got yellow, yellow, or I've got yellow, green, or green, yellow, or green, green. So what should I do with those probabilities? Add them together, yep. If you've got, because at the end of the experiment, we've just got 2 marbles. Right? It can't be that both of these are happening at the same time. It either happens that way, so 2 over 90 plus 10 over 90, 10 over 90, 20 over 90. So adding fractions, see why I kept the 90. You have to have the same denominator anyway, so yeah, just leave them 90. How many do you end up with? 2, 10, 32? Yeah. If you want to, 42, thank you. If you want to reduce that at the end, you can, or if you want to look at it like that's almost 50%, right? So quite a bit of the time you're going to get no red. What's the probability you get at least 1 red? What's at least 1 mean? 1 or? Yeah. In this case, 2 would be our cutoff, 1 or 2. That's got 2, 1, 1, 1. It's the what of 0 red? Remember the name for that? Complement, yeah. Yeah, it's either there's no red or there's at least 1 red. It's got to be one or the other. So you could just go back to this one and say, well, how many did I leave out? 48? Yeah. So you could do 90 over 90 minus the 42 you already did. Yeah. That would be just one way to do it. Those 2 are complements. But you could always go back in and just add up the ones that I underlined. Right, anything with a red in it. Okay, last question. What's the probability I'm all done and I got 2 of the same color? I already know it's going to be over 90, right? So how many of them have the same? So I need the red, red, yellow, yellow, green, green. Red, red was 6. There's 2 more. So 28? Yeah. Okay. Okay, any questions on that? All right, that's it. Thank you.